put it in the pocket. All right, thank you for inviting me to give the talk here, and thanks for staying back for the last talk. So I think that it's already 4:40, so I think it's going to be short. So this is a joint work with Pawan Aduri from Iowa State University, Kuldeep and Arnab from National University of Singapore, and myself from University of Nebraska, Lincoln. Okay. So a SAT problem. Here you have a formula in CNF form, and SAT is asking, given this formula, decide whether there is a truth assignment to the variable so that f is evaluated true or false. But if you step back and think about this in the Boolean, in the logic setting, so what we are asking is the following set that we have this Boolean ring, and we can interpret and an or function as natural we do, and then we can also try to order these elements, 0 being less than 1. And in this setting, you are asking, given a Boolean formula, compute the maximum value or interpretation of this formula over all interpretations, which is a mapping from the variables to the Boolean set. So here, X is the set of variables, and pi f is the natural extension of pi to f. So I will use this pi notation throughout this talk. So in this formulation, of course, f is satisfiable if and only if max overall interpretations pi f is 1. So of course, this is the same, nothing new I added here, but I think that a good thing to view this the SAT in this form is to actually now you can try to think of what about other interpretations. So in particular, here is one semiring, which is a very well-known semiring called Viterbi semiring. So here is the set is interval 0, 1, real interval 0, 1. And let's say that we with this natural order, which is inherited from the real numbers. And then you can imagine AND operation as the multiplication and or as the max. And I'll throw in this negation interpretation, which is not x is 1 minus x. And I'll come back to that. And then in this, and then you can ask this question, of course, now, given this formula, compute maximum value of any interpretation or all possible interpretation. Right, so you can do this calculation here for this formula. So, you can distribute, and it becomes max of x1, x2 into 1 minus x1 or x1, x2, 1 minus x2. And you can see that this takes the optimum value at x1 equal to 0.5, x2 equal to 1, and the value, max value it takes is 0.25. And of course, there is other interpretations as well, which is maximizes this. But a good thing is that even in this interpretation, if it's satisfiable, if and only if it is evaluates maximum value as to 1. So notice that here the formula was not satisfiable, but we did get something other than 0. So there is probably some valuable information here gained by this particular interpretation. So just going back to this negation, of course, there is no negation of the semiring. So we have to kind of come up with, so you can ask, what is this, what is the meaning of this negation? So for this work, we didn't really attach any meaning to this. Most of the things we assume the minimal, a function which satisfies this minimal condition that negation of x should be x and negation of 0 is 1. So, but rest of the talk, I'll only focus on x, negation of x takes equal to 1 minus x. And you can ask this question for any semiring, and then there are some of the useful semirings which people have considered in various settings. In particular, our interest came from the data provenance in the database community, where you interpret these as confidence scores and can associate some meaning to that. But we abstract those things out in this study. So, but my point is that it is actually being very useful in various settings. And there is this access control semiring, which also has been useful in security specifications, where you can think of every I in K associated with an access control level with the natural ordering, where 0 corresponds to everybody has access and K corresponds to no access at all. So just giving you an order in the access, and then you can specify security systems with this one.
I have a question.
Yeah.
Did I understand right? You interpret negation as 1 minus x?
No, so here we not as 1 minus x. So in this particular case, you can actually K minus x. So
K minus x.
Yeah.
Okay.
Yeah. So again,
K plus 1 minus.
yeah. So our results doesn't really depend on what interpretation. It's some natural interpretation results.
Yeah.
Yeah. So that's a good question. What kind of negation makes sense? I think that we discussed this a lot, and it really depends on where the application is coming from. With this, so this is the computational problem we formulated. So we call this opt-sem-val, optimum value for a over every interpretation, and sem stands for semantics. Okay, so that's the problem. So the problem is, let's fix some semiring, and now the question is given a formula, and I'll assume it's given in negation normal form, and compute the maximum overall interpretation pi of that. It's a computation problem. Actually extends SAT. That's a beyond SAT. And what we did, we didn't know anything about, especially we started with the Viterbi semiring, so we didn't know anything about its complexity. So we started investigating what will be the complexity of this problem. And as I mentioned, it's at least NP hard, because it's satisfiable if and only if this evaluates to 1 for Viterbi semiring. So what we showed is this particular upper and lower bound. So we showed that over Viterbi interpretation, it is at least as hard as FP to the NP log, which is the class of problem which can be solved in polynomial time with log many queries to satisfiability, or equivalently parallel queries to satisfiability. And we give an algorithm which runs in polynomial time with SAT queries. That's the main result, so to say, what we came up. And we could show other things too. So for other more finite cases like access control, this boils down to equivalent to SAT. So it's nothing additional in terms of the complexity. So what I'm going to do the next 2 slides, this is 1 slide, but it's going to show, is to show a proof, not the entire proof, but the outline of the proof. And the reason is that it's kind of interesting. Some of the things seems to be more general than just the proof itself. So, so what we showed is that, okay, we can reduce the max SAT to opt-sem-val. And max SAT is the problem. You're given a Boolean formula in CNF form. You wanted to compute the maximum SAT number of satisfiable clauses. And it is known that this is FP to the NP log complete. Problem in FP and NP log complete, and you reduce it to this. So I think that one of the interesting lemma came out of this is this particular lemma, which says that if I have a Fn formula in CNF form with M clauses, and let R be the maximum number of satisfied clauses over the Boolean ring, then any Viterbi interpretation, the value is going to be less than 1 by 4 to the m minus r. So it is somewhat independent of anything. It is just very general. So I put confidence bounding because, again, coming from the Viterbi interpretation, there's some meaning of confidence, etc. So it's basically saying that for if I have a max at instance with R being the maximum number of satisfiable clauses, then you cannot get better than 1 over. It's uses some combinatorial, not combinatorial, it's basic analysis of this formula. So, and then once this is then, the reduction is pretty easy. So I can show that. So what we will do is you take a formula F, CNF form, we will add this clause for every clause in the CNF F formula F, we will introduce CI union Y as a new variable. So you add M new variable and also throw in the negations of those. Then we can actually show that this is exactly 1 over 4 to the m to the r, the opt-sum val, or the optimum value it can take is 1 over 4 to the m minus r, where r is the number of satisfiable clauses of it. And the way we'll do that is that we can actually give an interpretation phi, so that pi f star, pi f prime is 1 over 4 to the m minus r. And because of the confidence bounding lemma, it's the best possible because the new formula has 2m clauses and m plus r clauses can be satisfied. So therefore, it is a reduction because I can actually now solve opt-sum val on f prime and get the value and compute r. And the upper bound is connects to something else. And so, of course, we wanted to show something like fp to the np. The usually idea is to you define a binary search language and search for this in exponential space using an NP language. So we define this LOB language, which is formula and some value, and that's in the language if it's greater than the value. Of course, the main challenge is that, again, these interpretations are on 0, 1. So what if this value is irrational or things like, it's still possible. It doesn't exclude such possibilities. But what we can claim is that actually this falls in this sequence called Faraday sequence over, so f script fn with n as in 2 to the polynomial in the size of the formula. Faraday sequences of order n are fractions of the form a by b, where a and b are less than or equal to n and GCD of a b is 1. So it's, in fact, when we started looking at it, it's very well studied. Algorithms for Faraday sequences are surprisingly somewhat difficult even to get rank of an element in the Faraday sequence, etc. So I think that's kind of interesting that this popped up in this particular upper bound. And of course, there are other technical challenges, but once we have the proof, the claim that it doesn't be arbitrary, we can actually go through the rest of the proof without much with some work. So I also looked at this approximation problem of how close you can approximate. You can get an upper bound which is 0.76716 to the m approximation for 3 CNF formulas, M clauses. We can actually get it for any CNF, but then the expression will not be this nice. And we can show that it's also hard to approximate beyond 0.845. And that's the technical, the content of the results I wanted to present. And of course, there are these technical questions. We thought about it. Is it, we cannot still conclude which way to go, whether it is closer to the max hat or it's close to the lex first hat, because we just end up with the NP. So we don't know where it actually, and of course, if it has to be useful, of course, we have to come up with some algorithm. So that's can we use SAT solvers or to actually get useful information about Of course, the non-technical question is to why is this problem useful? Is this problem make sense? And our research came from, in fact, the database connection I mentioned. We were looking at provenance, and that's how we defined this problem extra. So it seems like there is an increasing interest beyond Boolean interpretations in database. In fact, the next semester we have this program, logic and algorithms in database theory and AI, and one of the themes is extensions of logic to semirings. And that's it. So I think
let me go back to negation.
all right. Okay.
I have a suggestion how you could interpret this. So this is what's done sometimes in finite model theory. People are also looking at finite structures whose atoms are labeled by elements from some semiring. And then what they look at is what they call model defining assignments. So that means an assignment to every atom and every negated atom, an assignment of a value from the semiring in such a way that at least one between the atom and the negated atom is 0. Okay, and then you can ask the question, maximize over model defining assignments.
I see. So that's a natural negation which has been considered in the semiring situation.
Provided it's in negation normal form. Yeah.
Negation,
What you lose when you go to semiring semantics is the classical equivalence of first order logic go away.
Goes away.
Right. Just
I
anything
see.
you can imagine, the implication being the disjunction of negation, all these things go away unless you define them.
I see.
So you have to be very careful. You have to work with negation normal form.
Yeah, so that's what we have. We realize that we need to work with negation normal form. So all the things we have, but then it might be difficult to
There is a very nice introduction to the semiring semantics for first order logic. It's a still archive paper by Gredel and Tannen that came out of the 2016 program here.
I see. Yeah, I think we must have seen this. Yeah, but I think that we'll talk about that negation a little bit more closely. Yeah.
I just wanted to add, so Tannen is who gave us,
that's true.
who introduced us to the, and this problem we were motivated from reverse provenance analysis, which is discussed in the
we were
Gredel-Tannen paper. So.
Oh, you don't have.
No, you were
okay. I
great.
thought.
No, it was like I put this and then I was preparing to clap.
Oh, I see.
Okay, then.
I'd like to thank, sorry.